Finally, let us discuss the rational functions whose denominators are cubic or higher. In that case, the shortcut method we talked about for quadratic functions or quadratic denominators do not apply, so we'll have to do something like this. Well, factor the denominator, that's the same, and then we'll have to set up A1, A2, A3, something like that for each multiplicity, and then for different ones. And consequently, we're going to end up with a lot of coefficients and consequently rather humongous system of linear equations. What if we have quadratic irreducible factor? Then you're going to get ax plus b, not just one number, but we have to have a linear function over there. If that has some multiplicity, then you have a1x plus b1, a2x plus b2, all the way up to anx plus bn, so we're going to get something really complicated. Let's see how our textbook author dealt with that kind of situation. What if we have x squared times x minus 1 cubed as denominator? In that case, we have x squared, those two, and a and b, and x minus 1, x minus 1 squared, x minus 1 cubed, and those for c, d, and e, and take all these together and then set up a system of what? 5 equations, and you have to solve for a, b, c, d, and e. Well, that's really complicated thing to do. Well, here's a little bit simple example, but this one is already complicated. X cubed minus x squared minus x plus 1 is denominator, and this one is not a trinomial, so it's far more complicated, far more difficult to factor. Here in this textbook, our textbook author decided to use this factor theorem. Q of x is denominator, plug in q of 1, and you're going to get 1 cubed minus 1 squared minus 1 plus 1, so that's 0. So x minus 1 is a factor. Divide this denominator by x minus 1, and the quotient is x squared minus 1, and then factor further, so you get something like this. Personally, that's not the way I would have approached this kind of problem. I would have much preferred to use factor by grouping in this case. Okay, let's see. So denominator is x cubed minus x squared minus x plus 1. Okay, I don't need this screen anymore, so let's make it even bigger. And I'm going to group this one and then that one. So what do we have? First group, we have common factor x squared. So x squared and x minus 1, that comes from the first. And a minus x minus 1, that comes from the second. So x cubed minus x squared is this one. And then minus x plus 1 is that one. And then I have common factor x minus 1. So x squared minus 1, x minus 1, because x minus 1 is common here and there. And then finally, I can factor x squared minus 1, x plus 1, x minus 1, and x minus 1 was there before. So combining these two, I'm going to get x minus 1 squared. This, I think, is a little bit better than the way we did in the textbook here. In any case, we have the factorization. And then what do we have? We have to set up an equation. a over x minus 1, b over x minus 1 total quantity squared, c over x plus 1. And set up the equation, set up the system of equation, and then manipulate the numerator, take the common denominator, manipulate the numerator, and then compare the coefficient, and we have the system of 3 equations. And you can find out a, b, and c value. Consequently, we have, well, this decomposition, and then this integral. Wow. So here's my dilemma. Writing this kind of problem in any kind of exam or quiz is not realistic. They're just too long, and each individual process is just elementary. So I don't think this is really testing too much. And okay, I admit it. I've been teaching in college level since 1994, and I've never written this kind of problem. I rarely write decomposition by partial fraction to begin with, and if I do, I stick to quadratic denominator that can be held by this shortcut formula we discussed. Well, this problem, example 4, is talking about quadratic irreducible factor. X squared plus 4, that's quadratic irreducible. So we have to have bx plus c in numerator. And then, again, hard part is to get the common denominator and then manipulate the numerator and then compare the coefficient to get system of linear equations. And solving it, we get, well, a is 1, b is 1, c is -1. And these 2 or 3 lines actually will be fully equivalent to 1 or 2 full pages if you actually write everything down. In the end, we have arctangent function from the quadratic irreducible factor. Okay, any more? Okay, even more. Repeated irreducible quadratic factor. Well, we can consider these kind of problems, and if you have some time to burn, try to follow through these textbooks. There's a lot of skipped steps, so you'll have to spend a lot of time filling everything in. Factorization, solving the system of linear equations, and so on. Okay, rationalization. Okay, taking u substitution as a square root. We discussed that in the previous video, and that's about it. Let's see, is there anything more that I have to emphasize? Okay, let's go to my notebook and let's see if I have some more optional topics. Okay, these are pretty similar to textbook's method. We have to set up those A, B, C and then solve that. For the problem, we have to get A, B, C, D and solve those. In these cases, we'll have to do appropriate substitution, and that substitution will typically be the square root, and then you'll have to do a bit of a partial fraction in the end. Exactly how? Well, I'm gonna leave those to you. You can always open up and see the answer key, but try to do those without looking at the answer key. Again, entire section 3, this high order part, is actually an optional topic, so if you just go through the answer key directly, well, I'm not going to blame you. Some trigonometric functions. T is tangent of half of x, and you can use the half angle for double angle formula, and then you're going to end up with a rational function. This is typical deal. T is tangent of half of x, and dt is 1/2 secant squared. And then secant squared is interchangeable with tangent squared, right? 1 plus tangent squared. So we end up with 1 plus t squared over 2. Consequently, dx will be 2 over 1 plus t squared dt. So we ended up with a denominator. And then cosine and sine are given by this double angle or half angle formula, kind of like this. And that, so plugging everything in, you're gonna get a integral of a rational function. So sine of x is that, and then we end up with a rational function, as you see over there, and go through it all the processes, and you're gonna have two logarithmic functions, and then they are logarithmic functions of tangent functions. Let's see, do we have similar kind of integral there? Well, here obviously the integral Mathematica will produce probably will not resemble what we're gonna see, so I just want you to verify the backward. I just start from the end and then take the derivative and simplify it till I get the original function back. Yes, indeed. Well, everything is optional, so if you have some time to burn or really challenge yourself, you can go through with those. By the way, this kind of substitution, tangent as half of x, is very, very powerful methods to calculate a lot of trigonometric integrals. The next example is done pretty much similar fashion. Final problem, volume of a solid. Okay, it's nothing more than just oh, excuse me, that's different. We already saw much simpler problem that is given by cylindrical shell method, rotation by y-axis, this time rotation by x-axis. So we have to take denominator squared, and denominator squared we get something like that. So we have to set a, b, c, and d, because you see a over x plus 2, b over x plus 2 squared, c over x plus 1, d over x plus 2 squared, and then set up this system of linear equation and solve those, and you're gonna get 2, 1, negative 2, and 1 respectively. And then you can go through with this computation. This looks short, but a lot of steps are hidden, so this is actually a very, very long problem too. In the end, we have covered pretty much everything, almost like a blanket, yes, but let me emphasize again, the entire third video is optional video. We're talking about the higher order case. So my suggestion to you is concentrate upon the quadratic case, especially this 2.1, these problems where you can apply the shortcut formulae 1.1 and 1.2 in straightforward fashion. And then if you're gonna go a little bit further, then these kind of problems, 2.2 and 2.3, with a bit of a substitution will give you quite a bit of challenge. 2.4, I think these kind of problems exceed the kind of level I'm gonna set for this course. And 2.5, this one's okay. As a matter of fact, in our textbook, there are some cylindrical shell problems that are okay. And hopefully WebAssign also picks up those kind of problems too. That concludes 7.4, integration by partial fraction.